Mathematicians, it's Miss Cattey here with another video. Today we're going to talk about composite area. In our last video, we talked about the area of various figures that are two-dimensional, flat figures like squares, rectangles, triangles. We had our regular polygons in there. Today we're going to take those figures and combine them into more complex shapes. So all a composite figure is a figure that's made up of other simple figures, and we can find their area in that way. So our first example is going to be this image that looks sort of like an ice cream cone. We've got two pieces here, and our first step is going to be to identify those. So here on the top, we have a semicircle. And then down here on the bottom, we've got a triangle. So that means that we have a total area that is a semicircle plus a triangle. And we know how to find both of those areas on their own from our video from Monday. So a semicircle is going to be half pi r squared. And then we're going to add in our triangle. That's half of the base and height of that triangle. Now what you need to be careful of here is that when we've got composite figures, their heights are not always going to be the same. So I like to color code to make sure that I'm keeping my pieces together. Or if you want, you could find the semicircle on its own and then find the triangle on its own and then add them together at the very end. That may be a strategy you like as well. Now, we're going to start with our semicircle. This 16 is not our radius. That's our diameter. And think back to Monday, where we found that the radius was half of the diameter. We know this from circles from 8th grade. So this is just a review. Here my diameter is 16 meters. So that means my radius is 8. That means that this little segment right here is 8 centimeters. Okay? Now we're going to use that information over here in our formula, 1/2 pi, and our radius is 8 squared. That's the first half of our total area calculation. The second half is our triangle. Now we need the base and the height of that triangle. I'm going to switch colors over in the diagram. The base is right here. That's going to be our full 16 meters. But we don't yet know our height. We know it's got to be perpendicular, but we don't know what it is yet. Now, this height is a right angle, which means that we've created right here a nice right triangle that will allow us to use the Pythagorean theorem in order to find that missing height. Okay, so I know my hypotenuse is across from my right angle, so that's got to be C. A and B don't really matter. I'm going to leave this one as H just because that's what it's going to be in the end. So if we're using our Pythagorean theorem, I'm going to move, I'm just going to leave it here. So I know A is 8. My B, I said I was going to leave it as H squared. And then we have 17 squared. Well, our goal is to get H by itself. These cancel. I'm going to move over here. Now I have H squared equals 17 squared minus 8 squared. We don't want to combine them once they've got those squares on them. 289 minus 64 is 225. And then we can take the square root of both sides, and we now know that our height is 15 meters. I'm going to plug that in up here, substitute that into our formula, and now we are ready to finish this guy up. Now my 1/2 pi 8 squared is going to give me a semicircle area of 220.53 meters. And my triangle, that 1/2 16 times 15, will give us an area, oh, sorry. Got a little ahead of myself here. Gives us an area of 100.53. And this gives us an area of 120 from the triangle. Our last step is going to be to go ahead and add those two areas together. And this is where we get our 220.53 meters squared. It's area, so we want to square that unit. That's our total area. We just broke it into a semicircle and a triangle, and we added those together. For this next example, I'm not going to go through the entire calculation because you guys are capable of doing that. You have our video covering the formulas. We're just going to decompose this shape. We're going to take it apart. I'm going to go left to right. Here I've got a semicircle. I know it's not really a full circle because over here we've got a sharp 90-degree angle. So instead of having to try to figure out that sliver, I'm going to say I've got a semicircle first. Now, over here, we have a really nice familiar shape. We've got a triangle in green. And the last section right here is now a rectangle. So you might notice that up here, we're not given the height of the pieces individually. We're given that total 55 meters. You're going to have to break that up and figure out how much of that is attributed to the triangle, how much is here at the rectangle, how much is part of this semicircle. And for that, you're going to use your properties of your figures. Now, when we've got our total area of semicircle plus triangle plus rectangle, you should find an area of 745.3 millimeters. Remember, those are the small segments on the centimeter side of the ruler, the really tiny ones. 745.3 millimeters squared. I would really encourage you to try this example on your own and check your work with this answer. Let us know if you need help. Okay, so in all of these examples, we were combining areas. We had two or three pieces that we are clumping together to form a bigger shape. Now that's pretty simple. We can pretty intuitively see that. But there's a second kind of composite figure. This type of figure, we are going to be asked to find the area of the shaded region. Now the shaded region is not the whole shape. It's not a normal figure. It is part of another figure. Now in the last one, we added those two segments together, but here we're going to want to get rid of, or those two sections, not segments. We're going to want to get rid of this triangle. It's cutting a piece out of our rectangle. We want to know what the area of the green is when we chop out that red part. So this is similar to the last one, but for our shaded region, I'm going to use the subscript S for shaded instead of T for total. We want to find a rectangle. Now minus a triangle. We want to chop that triangle out. We're getting rid of that in our shape. Okay? So the rectangle is the outer figure. That's why we are starting with that one. We have a big rectangle and we're trying to cut out that triangle. If we flip that equation around and we try to subtract the rectangle from the triangle, we're going to get a negative value for area, which is not a reasonable solution. So if you get a negative area, go back and double check your work, see what you did. Okay, so our shaded area is our rectangle minus our triangle. I'm going to call this B2 and H2 because my triangles, I guess I'll call these 1, because my triangle's base is not necessarily the same as my rectangle's base. Over here, this is my B1 of my rectangle. Here's my H1 of my rectangle. But over here, the height of my triangle and the base of my triangle are a little different. My H2 is 11. And my B2 is this side. Because this is a rectangle, we know they're congruent, so this has to be 25. So you just want to be careful. This might be one where maybe you find the area separately and then bring them together at the end. That way you don't confuse your variables. This B and this B are not the same. Okay, we're talking about different figures here. But our shaded area for that rectangle, I'm going to substitute in my values. Minus half. My triangle's base is 25. My triangle's height is 11. And that gives us a final area here for this figure of 212.5 centimeters squared. That's my shaded region. Okay, the total of the rectangle that is now removing this red piece. We sliced it out. So that's our shaded region right there. Okay. Last one, just like the second example of the composite additive figure, I'm not going to go through the whole thing. We're just going to do an overview. Our shaded area here is on the outside a square. How do I know that it's a square? That is going to be because of this inscribed triangle, or circle, I'm sorry, this inscribed circle that we're eventually going to get rid of. If it is 25 feet wide for this figure on the outside, that's the diameter of the circle. That means that this diameter vertically has to also be 25 feet. And because it's not chopping into the circle anywhere or not perfectly reaching, this guy is our square. So we've got a square minus a circle here. Again, I'm going to recommend that you go through and check this example, but you should get a shaded area of 134.4 feet squared. These are our composite figures, and this is what we're going to use on your assignment for today that's going to be due on Thursday by 10 p.m. So there are some big takeaways from this topic that I want you to keep in mind while you're working. First one being composite figures are decomposed. We break them up into more familiar, more simple shapes. So we're going to take those and we're going to chop them up in order to find their area. Whether we are adding those pieces together like we did in the first two examples, or cutting out a piece of an outer shape. Either way, we broke it into stuff that was more familiar. Now, in our shaded region figures, we want to remove things using subtraction. We have our additive problems where we're putting things together, and we have our subtractive problems like the last two examples where we're taking out that circle, we're taking out a square. So be careful, pause before you just add all your areas together, because in this case, we didn't want to add it all. Now, if you guys have any questions, if you need help or assistance, text us on Remind, attend one of our live tutoring sessions. Remember that tutoring schedule with the links is available on Google Classroom. If you can attend one of those sessions, let us know and we will try to schedule something with you individually. But other than that, have a great day. Make good choices. If you don't, learn from your mistakes, and we look forward to talking to you in the next video. Have a good day.